okay? And I'm gonna go ahead and share my screen to the Jupyter Notebook. So there it is. You should be seeing the Jupyter Notebook. I already have the page loaded. Hope it didn't die out on me. Okay, good. All right, so today we're just going to continue with what we were doing last week, right? So if you remember last week, we were building basically a KNN type of classifier with, PyTorch and FastAI. So if you remember, oops. Okay. I forgot to do, hold on. I forgot to start the environment, I think. Give me a sec. Sharing. All right, so I'm going to go back to that script. So it was fundamentals. Okay, so now if I run this one, you should be seeing the Jupyter Notebook. Okay, it found, okay, good. It found FastAI. And then we can run all of this. You're gonna need the script from last week, because if you're, the important thing is the data, right? So we had brought in the train 3s and 7s, and from validation also 3s and 7s. So we want to reuse that data or continue to use it. Now, if you remember, the issue was that we in the previous lecture, we built a type of a KNN. So there was no actual, learning of weights. We weren't learning a model with weights, etc. We were just basically calculating these distances, right? Do you guys remember that? So we calculated distances, and then we talked about how you would take pictures of your family and then get an average of that and then compare everyone to the average. But in this case, we are now ready to move on to understand the framework of, let's say, a neural network, right? And how a neural network will train instead of using KNN. So basically, we're repeating the same exercise, but this time around with, and this is where we are, with sort of optimization, if you will. So let's think about it. Okay, so we're gonna start the code here. Okay, so we start with the same problem, right? And now we want to think, how can we train a new model? So let me switch over to the whiteboard here and just kind of illustrate what I mean. Just very briefly, you should be seeing the whiteboard. Okay, so let's think over here. We have, we had the images before, 7, 3. And basically our model was we had some average, etc., and we were measuring distances, right? But instead, what we want to do now is we want to create a model, we want to find some function. So basically, model is equal to some function, right? That given an input X is going to predict, the class of it. Is it a 7 or a 3? So that's the general framework that we want to consider. Now, we have basically two alternatives for the function, right? We have we just think of a function. Let's call it the quadratic function, for instance. That's just a function. Usually, I think it looks like x squared, ax squared plus bx plus c, right? So you probably remember that from school, and that has a specific shape called a quadratic shape. Another way could be if we just come up with a generic function, so something like wx plus b, right? And then we add nonlinearities by running this through another function g. Okay, so that's kind of the idea where we are. The two options that we have. Don't worry about these equations, just pick a function that already exists or create a general function, but learn these parameters, the w's and the b's. So the parameters are the w's and the b's, right? And we want to learn those parameters somehow, okay? And that's where the optimization and training comes in. So that's what we're going to take a look at today, is just this idea. So whereas this model had no weights or parameters, this one does have weights and parameters, which are these, okay? So that's the general idea here. So let's go back now to the script, and we're going to take it, slowly, easily here. So let's go and let's just think. So here we're going to take a look at a couple of ideas. So we're going to take a look at the idea of the training process. So the training process, right, which is going to be using something called stochastic gradient descent. And this is basically a type of a probabilistic approach to finding, solutions and optimizations, basically. So stochastic gradient descent. So we said the previous technique, the KNN type approach, does not learn weights for a model, but we will now look at stochastic gradient descent to learn these weights. So we want to look at stochastic gradient descent, SGD, to learn the parameters. Okay, so that's the goal. So let's just kind of motivate this idea of what we're talking about. So, we're going to call from FastAI, and I had to install this. I think it was just pip install a fast book. Okay, so I'm going to say from, so it was most likely, if I remember correctly, pip install fast book. Okay, so from fast book, this is just, it's just a show a graph really. So from fast book, import all. Okay, and now I'm going to do, we're going to create just a simple function. So let's call it f, takes in as parameter w. Okay, so f, w, and it'll return basically the w multiplied by something. So in this case, w2, which makes it a quadratic. So we'll see the effect of this when we plot it. So we can go over here and do plot function, f, comma, w, comma, cost determined by x to the power of 2. So we're creating a relationship there in the functions. You'll see in a second. We give it an input and it predicts a cost, basically, is what we're saying. So let's go ahead and run this. And there you can see it generates this function like this. So this is the function, the shape represented by this function. So when w is 0, the value is 0. When w is 1, the value is 1, basically. But then when the value is 2, the value is 4. So you can see it's growing in that direction. If it's negative, it's the same thing. The value is -1, it's 1. If the value is -2, it's 4. And so you can see this is called a quadratic function, Just has this kind of a shape like this, a bowl type of a shape. So it has a guaranteed, bottom, if you want to call it that. So usually when you do optimization problems, this is the function that you would love to have. You know, you remember that when you're learning, we're learning two things. So we have a function like this, y equal w times x plus b, right? But this function is also governed by another function, which is, it looks like in this example is this one. So basically what it means is this is the model that predicts, and then this is the function, let's say the loss function, which is the mechanism that we use to determine if some, oh, that should be it, to determine if something is, if we're learning or not, basically, if we're improving. So the idea is that you want to, if you look at this example here, if this is the cost representation, so you want this function, yeah, the goal is to reduce the cost, right? So here the cost is 4, here's the cost is 4. Really your objective is to reduce the cost to be almost close to 0, right? Which would be down here at this bottom. And so whenever we're training, we predict with this one, right? We predict with that one. And then we have a loss function that takes the y predicted and the y, let's call it real, right? Y real. And so it compares those two, the real labels to the predicted labels, and it tries to calculate some kind of a metric. Now, why is it quadratic? Because remember that the famous MSE that we've been looking at before, mean squared error, is also a quadratic function. So if we take a look at it, it just kind of looks like this. So, you know, y minus, you should be seeing the whiteboard, y minus y hat square, right? And that square is really what allows you to basically capture that. And then this is a sum and sometimes square root, something like that. But this quadratic here allows you to basically, you know, if this is your loss function, when you plot it, it kind of looks like that, okay? And this is just a classic example for linear regression. So I'm going to motivate it with that, but we're going to advance a little bit more beyond that loss function today. So if we go back now to the, code, we can see, so we've got the quadratic function defined there. And so really what happens is we want to achieve this weight. The question that might arise is, how do we adjust the weights to be the optimal one? So as we're going to learn intuitively, you can think of it as we have this mountain range, right? This valley. And we pick a W randomly. And the value is like right here or right here. So your goal is for the W to get down here. But the question is, when you find yourself here at this point, let's say, do you go down or do you go up? Because, you know, gravity does not apply here, right? Instead, you have to make a decision, and you're kind of doing this blindly. So you need to figure out a trick that allows you to say, oh, when I'm here, I should go down this way, you know, decrease W to the left. And if I'm here, then what I should do is I should increase W in that direction, right? So because you know where you are in the function. So there's something that we will use for that. And that's where the gradients come in, the so-called gradients in machine learning, the derivatives of basically calculating the derivative for every weight, every parameter of the function that you're using, the loss function, because the derivative gives you basically where you are. It gives you something called a tangent, which kind of indicates which direction to take. So the way that you can think about it is like this. Intuitively, we can think of this as the following. We're here in the function. You're right there. This is the parameter W. You're right here, right? And this is the cost. And then you want to figure out which way to go. So basically, in the way to think about calculus is that it calculates like a line like that. And if you're here, it calculates a line like that. If you're here, it calculates a line like that. So that tangent, the angle of it, basically tells you which direction to go because it's either like this, like that, or like that, right? And then this translates into giving you negative values, translates into giving you a value. It returns some value, we'll see. But the value could be -2 or 2. And so that, or 0, when it indicates that it's basically arrived at the point. So by having this value, now we'll be able to adjust some kind of an equation that does something like W minus learning rate times this value that we just got here. So if the value is -2, guess what? It makes it positive. If the value is +2, guess what? It makes it negative. You see, and that's exactly how we know if we should go in that direction, or other directions. Does that make sense, guys?
Yep.
Oh,
Okay. Oh, it does. Okay, I think you said it does. All right, great. So that's it. I mean, intuitively, that's the basic idea, and that's kind of what I'm going to sort of talk about now, but you understand the general framework of it, okay? So, or the general intuition. So, you know, this is the quadratic function, and so we want to, you know, the thing that makes these things like PyTorch and TensorFlow very powerful is that they do this very efficient, okay? That they calculate these so-called gradients, the derivatives of those parameters in a very efficient way. So we'll see that. But basically then, and we don't have to know calculus, you just have to be aware of it. So here calculus, right, we are, you know, the goal is getting the derivatives. Getting the derivatives, which are basically, you'll see in the language of this, is called the gradients. So this is going to be the gradients. Okay. So in deep learning, gradient usually means the value of a function's derivative at a particular argument value. Okay, so let's just think of that definition. So in deep learning, gradient usually means the value of a function's derivative at a particular argument value, the weight. So really, you know, we associate gradients that we want gradients not with the function, but with the variables themselves. Okay, so the focus is on the variable, you know, that is the tensors. So the focus of the gradient is on the variables and not the function. So in this case, it would be basically, it would not be on the function itself, but it would only be on the W parameter, right? The W parameter that we plugged in here. That's where we assign the gradient. So the focus of the gradient is on the variables and not the function. Okay. So let's think a little bit about this. So now we have the, you know, let's say just here we're just kind of playing with this. Let's think we have a function. Let's say the same function we had before, f, and it takes a parameter w, colon. And then the function that we have is return, w, right, like that, right? So return, that's the same quadratic function that we have. And then we're going to create an input, right, that goes into this function. So xt, let's call it a tensor, right? So that's tensor 3. This 3 float. But whenever you do this, whenever you have something like this parameter, and And actually it should be W, but let's just leave it at X. And here is where in PyTorch, you have to say, what is the thing that is going to get, that you have the gradient basically, right? The values that need to be adjusted. So in this case, here we say requires grad, okay? And notice how it's written. This is basically what it tells. Once you're mapping everything, all the variables and all the functions and everything, when you are in the process of learning, you can just say backprop, and then PyTorch will know, oh, this is the gradient because it requires grad, and so it's going to compute the values, right? And that way it can make the adjustment. So basically, let's think about it here. So if I have an X input, right, and then I have a YT, which is the predicted value. So then F XT is the input in the function to YT over here. Okay. So now we can print out this value YT. Let's do print YT and run it. And you can see it gives you a 9 because it's 3 to the power of 2. 3 times 3 is 9. Okay, but we can see here that it says backward, right? So it basically indicates that this is a thing that when you do back propagation, you're going to calculate the derivatives, the gradients, and then basically we'll be able to perform this process over here. Does this idea make sense so far, guys?
Yeah.
All right. Good. All right. So go back to the code. So we have that there, and we can see that we have the gradient word there. So now, to tell PyTorch to calculate the gradients, say now tell PyTorch to calculate the gradient. Okay, so to do that, it'll be YT dot backward. And this just basically assumes, okay, I took the function, I predicted the outputs, right? And then now I'm going to take those outputs, compare them to the labels, and I'm going to work my way back and calculate the gradients so that I can adjust the weights. Here, we're just doing a simplified version of this. So now that we've done this, if we want to look at the gradients, what we can do is we do print. We do print, and the value that we're going to print out is actually XT, but what we want is its gradient, okay, which is stored here by PyTorch, okay, for it to be used. So if I run this one, it gives me a 6. You see that? And that's actually the result of calculating the derivative. So if we look at this like on the whiteboard, we do the math of it, the problem is simple enough, right, that we have here so we have here in math the function. So in math, the function was x like this, right? So this was the Python code. So this is really equivalent to x squared, right? That's the function. If we take the derivative of this, which we, it's very simple. Derivatives are just a process, kind of algebraic. So here then the derivative of x2 is actually 2x, right? So you would do something where you say, okay, what's the derivative of x2? It's 2x. Usually the 2, the exponent becomes the number in front of it and goes down by 1. So 2 minus 1. So 2x1 really. All right. So, but that happened. And so if the variable was, so if x was 3, I think it was, then now we plug in 2x to 3, and that's 6. You can see, so it gave us the same 6 that we were able to get in the in the Jupyter notebook. Okay, so we have the 6 there. You guys see that? So basically, this also gave us the value. Okay, and like I said, we want to use these values to adjust. If we go back, we want to use these values to adjust the weights themselves. Okay, that's basically the goal. And so now we're going to proceed. Now let's think. Let's repeat the same process. Let us repeat the same process, but with more variables. So usually we're not just going to have one weight, right? We're going to have, you know, a matrix of weights. So let's just try it with like a vector of 3 weights. Let us repeat the same process, but with a vector of 3. And just to see how it would work. So then we can create so let's do xt tensor and now this tensor is, you know, we're just going to make a vector of 3.0. These are the initial values. Then 4.0, you know, 4 point float. Then 10. Okay, so 3 values. Okay, and then we're gonna assign to this again, because these are the weights. This is the important thing. We're gonna say requires grad. Okay, to imply that this is the thing that we need to calculate derivatives for. So again, we're going to use the same function. We're just going to modify it a little bit just so that this works. So we can do the calculation. So f x colon return x to the power of 2. And now the only thing that we're going to do is, because we have 3 of these, we want to sum them just so that we can calculate the values. So sum all 3 values. So now we repeat the same thing we did before. We calculate yt given the function. So I'm going to say f xt. F xt gives me yt. And now we can print yt just to see the value. Basically, the answer should be 9, should be 16, and no, sorry, it should be the sum of it all, right? So let's just take a look. Yeah, so 125 is the value, so it just adds it up there. Okay, and we have the original ones as well, which are 3, 4, and 10. But now what we want to do is we want to calculate yt, the gradients. So that means yt dot backward. So we do the back propagation, which is basically, remember, we do a pass to the front to calculate the values compared to the real labels, then we go back. Right? So yt backward, like that. And then print xt dot grad, just to see what the derivatives of this should be. And they are 6, 8, and 20, which makes sense because the derivative of this function is 2 to the x, right? So the inputs are 6. So basically 3 times 2 is 6, 4 times 2 is 8, and 10 times 2 is 20. Okay, and there you go. That's kind of how, that's actually pretty nice, because I've shown you pretty much the basic mechanism of how PyTorch does it, right? Where it takes a function, some variables, and then you just tell it to do the grad, that what the grad is, and then tell it backward, and it calculates the gradients, which are the things that are going to adjust the things that are going to adjust the weights. I'm going to try negative here. So let's run it. And then we have a value, so it kind of tells you within the equation sort of where things are. Any questions, guys? Any questions?
No questions.
So now that we've printed out the values, now we need to use xt grad to adjust the weights, right? So that's the next thing. So we have these values, but now we need to adjust the weights. So here we can say, so now we use xt.grad to adjust. Okay, so we want to adjust the weights. So how do we do that? Here comes in the very important and actually very simple function for updating the weights. So it's usually just something like this, minus, and then here we're going to specify, we have a learning rate. Remember, the learning rate just is a parameter that tells you how much you should multiply the adjustment, right? So you guys, I think, Jason today showed the sweet spot for the learning rate, right? So not too big, not too small, the Goldilocks, if you will, right? Not too big, not too small, to figure out where figure out which learning rate is the best to find the optimal result. Okay, imagine it again like a giant crossing mountains. So if the learning rate is too big, they take too big of a step and they may miss the valley altogether. If it's too small, they'll go down the valley, but it's going to take them forever, right? So you have to kind of play with that. And then this learning rate will be multiplied by xt.grad, which in particular, what's important is that symbol, right? Does it make this negative or positive? And that's kind of what's really important. So that's kind of the idea. So let's go ahead and think of a model here. Let's think of a model where we don't have to, where we just pick the equation, right? So if you remember in the whiteboard, I said that we can either, to determine the function that we're going to use, we can either pick a function or actually use a generic function and learn the way, what the function should be. In this case, we can just pick to use a quadratic, for instance. Right, so we can go over here and just say that we're going to need that. We're going to basically, over time, we're going to look at some behavior. Okay, we're going to look at some behavior, and the behavior will be quadratic, for instance. So what that means is, let's say we have a model. We define a model. We define a model of how the speed of a roller coaster, changes over time. Okay, and we just say that, let's say every 20 seconds or so. So first of all, let's create a variable called time that's got, the intervals or the amount, 20 seconds. So we're going to do torch dot a range a range from 0, comma to 20. And then dot float. Okay, so we're going to generate these values first. We're going to print this. So I'm just going to do print time. Okay, and we can take a look at this tensor. It's got some values, right? So we're going to plot these. These are the, over time, 20 seconds. We want to see something, right? So now we're going to create a function. And the function takes as input time, these intervals, and then we're going to plot it. All right, so let's do speed equals. And the function will be 0.75. It's just some function, could be anything. And then here we plug in time itself minus, let's say 9.5. And then, and this is squared, right? So what that's really the important parameter, that the behavior is going to be very quadratic. We could also add the bias plus something like 1. Okay, so if we have this function here, speed, if we plot it, let's just do plt dot scatter. And then we have here time, comma, speed. Okay, so I'm going to run this. I'm going to save it, actually. I'm going to run. And you can see I'm able to plot this behavior, right? So over the 20 samples, every time I give it one of these, it plugs in here, and it follows a kind of a quadratic behavior over here with some addition, some parameters. Where did this 0.75 come and where did this 9.5 come? They're kind of arbitrary and the +1, right? They're just to show something. Obviously, I picked this equation. I just wanted this equation because maybe I know the laws of physics and I know the laws of roller coasters. And the laws of roller coasters say that they're governed by this behavior. Now, in those measurements, there could be some noise. Also, maybe the equipment is faulty and it captures. So rand dn is a way that we can add a little bit of noise. Let's say 20 times 3 plus, and this is just to add a little bit of noise to the prediction. So you'll see what happens now. It's a little bit crooked, right? So it's a little bit crooked because of the noise, which represents just a little bit more of the reality of the world, right? So the world would have some noise in it, so it wouldn't be a perfect behavior. But anyway, this is an example of a function that we have actually just picked by hand. We didn't learn this one, right? We just picked it. And so that's kind of how that works. So from the graph, we know it is a quadratic function, right? So, we know this behavior is quadratic for the roller coaster. So now we could say, well, let's just train a model that's quadratic because it looks quadratic here to me. So then we can go ahead and really the quadratic function, as I showed you guys, the formal quadratic function looks like this one over here, ax squared plus bx plus c, right? So it means that I need to know what a, b, and c are, those parameters that are defined for that equation. So then let's start with that. We're going to try to see if PyTorch can learn those parameters. So we're going to define a function f. All right, and the function f will take t, which is the input time, and then it also takes params. All right, and params will be that a, b, and c. Okay, oops, that should not be commented on. All right, so we have this function 1, 2, 3, 4. So params will be A, comma B, comma C. We'll need to define it, but we're just passing it as params just because this is kind of a convention in PyTorch that you pass everything together as a set. And then we run this through the function return. And so the function, remember, we want to do A times X square plus B times X plus C, right? That's the equation we just saw before. We're just going to write it a little bit as PyTorch writes it. So in that case, or more Python-y, so the parameter is actually T, right? So T is our parameter. So we're going to replace this X with a T. So T square, let's put some parentheses in here also just for to say what should go with what. So A times T square plus, let's add another parentheses here, B times T, and then plus C, right? So the parameters come from here and T is the value. You see that, guys? So we're trying to model this with this, but we're gonna optimize. We don't know what A, B, and C are, so we're gonna try to optimize it. But in a similar way as PyTorch does it for neural networks. Does this make sense so far? So we are not letting PyTorch learn a neural network here, okay? Because we didn't define this to be a neural network, right? It's not a neural network. Instead, we are explicitly telling it, no, 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 don't use a neural network, just use this quadratic function. You know, that's kind of our, we're saying that we're not letting PyTorch figure out the function. Instead, we just pick a quadratic function, because remember that what neural networks are is they are universal function approximators, okay? So that's really what they are. So instead, we just pick some quadratic function, and we only need to learn the values A, B, and C. Okay, so now we do need to define. So now we need to define a loss function. So now we define a loss function which will compare predicted with actual values, right? So that we're still going to use, because this function will predict the value and then we're going to have some kind of real value, right? So that would be what we would want to do. So now we define a loss function which compares predicted to true and returns a value of the cost, right? So now we need to define a loss function which compares predicted values to true values, okay? And returns a cost value. So the lower is better, right? Lower is better. And here we can use MSE, mean MSE, okay? MSE stands for mean squared error, which is the one that we saw a second ago. Okay, so now that we have that, we can proceed to calculate this function, define MSE. Okay, so MSE takes preds, and it'll take also the targets or the real labels. Oops. And so it'll return, some kind of a difference, right? So in this case, we take preds minus targets, right? And we take the differences, we square them, look, again, this is a quadratic function, right? Just by this behavior, we know it looks like that. We know that it's going to have an optimal solution. So, and then for this, you know, because we have all the values, we just calculate the mean. And we're going to use that value as a measure of cost. Okay. So now let's test all of this. Okay, so I'm going to go ahead and test this. So let's, you know, we upload the functions. Okay, so I'm going to upload the functions. And now we define, let's go ahead and define the parameters. So define params A, comma, B, comma, C. Okay, so we define the parameters A, comma, B, comma, C. And these are the ones that we need to learn, basically. So let's initialize them as params. Torch.rand n. So torch.rand n. There's 3 of them, A, B, and C, so 3. So it's a vector of 3. And these are the ones that we're going to update, right? So requires grad. Requires grad. Okay, now given this, now we can go ahead and do a calculation. These values are currently random, but at least now we have values in A, B, and C. And given T, we can plot the figure, right? So let's go ahead and try to do that. So let's do, let's call the function. So we do preds equal F time, comma, params. Time, comma, params. Okay, so let's run that. Okay, so that's taken care of. Now we can go ahead and plot it and see what it looks like. Okay, we're going to compare the previous one. The time and speed, right? This one, the previous parameters that we had defined by this function with now our new quadratic function, which is trying to model the behavior. Do you guys understand? So I'm going to compare kind of this to what this predicts, right? So in this case, I had parameters for the function. Here, I'm learning them. So let's do that. So I'm going to do F time params. Now down here. Now plot the pred with random params. But hopefully, as we start learning, the graph will start to look better, right? So let's do, and this is just fancy plotting stuff. So show preds. But we need to put 2 scatters, one overlay them, one on top of each other. So I'm going to do show preds, and it takes preds, comma, and then let's say preds. Let's create an object that will hold subplots, so it can hold several things. So I'm going to do plt dot subplots. Okay. And then we have two plots here. The first one is the original one, scatter time and speed, right? Time and speed, speed in the time in the x-axis and speed in the y-axis, given, if we go up here, you know, given the function that we had defined over here manually. Okay, so we plot that one, and now we plot another one, ax dot scatter time, comma, 2 NP Freds to NP. Now, this is just to convert to NumPy and then put this in color red. Okay. And then finally, let's set some limits on the y-axis. Let's do ax dot set y limit equal to minus 300, comma 300. Okay, so hopefully this graph will look nice. So let me go ahead and save it and run it. And there you can see the blue line should be the real data. It looks kind of quadratic. Notice that this line is the opposite. Do you guys see that? The red line. Do you guys understand what we're doing?
Oh, yeah.
Yeah, so basically I'm trying to learn this function, right? The function, the red function should equal the blue function as much as possible. That's what I'm trying to learn. I'm trying to fit that model, okay? But the parameters are currently random, right? The parameters here, they're basically random values. So we need to adjust them via gradient descent. Okay, so it is currently 3:48. So we started at 2:30 to 3:30. Yeah, 3:48. So let's take a 10-minute break. Okay, I'll go ahead and save this. Stop sharing. And I'm going to go ahead and stop the